Hi, I'm Shamali Chatterjee. I'm an assistant professor in agricultural and biological engineering, and I lead ICAN. ICAN stands for the Innovatory for Cells and Neural Machines. ICAN has two thrusts. We have a computational genomics thrust, and we have an IoT and edge computing thrust. So let me tell you a little more about the IoT, that is Internet of Things and edge computing thrust of ICAN. The two thrusts in my lab are both typically using applications of machine learning. About ICAN's IoT thrust, we are interested in approximating these intensive machine learning algorithms so that they can run on lightweight sensor nodes. So we have various ways of approximating them. For example, we have an algorithm called ApproxDet that allows us to approximate computationally intensive object detection algorithms so that they can run on sensor nodes. Now, these sensor nodes do various measurements in these agricultural farms. For example, we measure soil moisture, soil temperature, nitrate, carbon, etc. And then these sensor nodes then talk to each other, and they also talk to the gateway node. Now, this gateway node is typically a Raspberry Pi, or it could be an NVIDIA Jetson class device. So you have these sensor nodes talking to each other and then relaying to the gateway node. Now, one of the things that we are doing is right now these gateway nodes are Raspberry Pis, but we are trying to change some of these gateway nodes to be these higher powered NVIDIA nodes. So I will show you some glimpses of the different components in our testbed and these NVIDIA Jetson nodes that can do computer vision on these nodes. To give you an example, an NVIDIA Xavier can run about 1/10 of the operations per second as the most powerful NVIDIA GPU that goes into the data centers. And each device, this NVIDIA Xavier, has 512 GPU cores and can process 11 trillion operations per second. So sort of supercomputers in the palm of your hands. And so we're looking to leverage some of this computation capability of these supercomputer style nodes, using these as the gateway nodes and replacing the lower compute Raspberry Pis with these new gateway nodes. I will tell you two stories today. One is Ambrosia, another is ApproxDet. And both of them are connected by the overall goal of my lab to onload computation on the sensor nodes rather than offloading computation onto the cloud. So we will call this onloading computation onto the sensor node as being on-device computation. The two aspects of on-device computation, one is that data transmission from these sensor nodes to the gateway nodes and cloud, they account for a large proportion of the energy expenditure by these nodes. So data transfer, for example, accounts for at least 85% of the total energy consumption and can be as high as 99%, depending on what data is being transmitted and what is the communication for the data transmission, whether it be LoRa, the long-range transmission, or BLE, Bluetooth Low Energy. So to give you an example for long-range communication, LoRa, if the data sent is reduced to 50%, the lifetime of the device increases by about 70%. That is 3.5 years to 6 years. And this is for low traffic intensity. But typically, you have high traffic intensity for a lot of these applications. So in that case, the lifetime increases by 300%. So 0.02 years to 0.08 years for the device. So this is a snapshot for Ambrosia, where we are decreasing the energy associated from this data transmission from the sensor nodes to the gateway nodes without compromising the error brought about by this decreased energy transmission. The other story is ApproxDet, where we are approximating object detection algorithms. So object detection is a kind of computer vision algorithm, and these are very beefy, that is computationally very hungry algorithms. And they essentially use lots of parameters in these neural networks. So what we are doing is we are using a data-driven modality to decrease the number of parameters in these neural networks. So now, in order to run these algorithms on these different embedded devices, now these embedded devices have have different technical specifications. Some are beefier than the others. Our algorithm, Proxtet, can use the right variant of the algorithm to map it to the computational resources at the back end of these embedded devices.
Okay, so here is a demo of a Proxtet, and you see that for the specific computer vision task we are doing object detection. So Proxtet, we measure the accuracy and latency, and you see that when there are no competing applications, so no contention, Proxtet does about as well as FRCNN plus MF. FRCNN is the leading edge object detection algorithm, and median flow is the leading tracker. So we see Proxtet is slightly better than FRCNN plus median flow in the absence of contention. Now, if you consider a case where you have resource contention on an embedded device, so this could be a mobile phone or it could be Jetson. Now, resource isolation on these embedded devices is inferior as opposed to server class machines. So you see that a Proxtet has an accuracy of 94% again, and in terms of latency, the latency shoots up initially, but because of the aggressive approximation by a Proxtet, the latency quickly recovers. In this case, latency, the lower, the better. However, you see in the case of FRCNN plus median flow, the accuracy is again about the same, but the latency stays high because it is not able to approximate. So essentially what a Proxtet is doing is for each frame, it is picking the minimum depth. So it is doing an aggressive approximation by picking the right approximation branch.
We have three different kinds of devices. The first one is NVIDIA Jetson Xavier, and the second one is NVIDIA Jetson TX2, and the third one is Raspberry Pi.
TigerStats is a tool developed by NVIDIA to report the memory usage and the processor usage of embedded devices, and JTOP is an open source tool on GitHub that helps visualize TigerStat data.
So I told you the story of Ambrosia, which is a data transmission reduction algorithm, and I told you the story of a Proxtet, which approximates object detection, which is a computational vision algorithm. And both of these are very relevant to the sensor nodes that are deployed in the farms in the WIN area. And funding is from National Science Foundation, from WIN, that is the Lilly Endowment, and from Army Research Laboratories. I feel like a testbed like this is very helpful to the outside world to simulate various conditions, whether it be conditions in the farm, whether it be conditions in the battlefield, or whether it be to deal with tele-robotic surgeries in the medical arena. With that, I'm very excited to present our testbed and the activities related to WIN in our lab, ICAN. Thank you.